I think we have to move to our last but not least speaker, Ashley Stewart, with his talk Building Robust Software with Automation, Containers, and Open Standards. Dr. Ashley is a postdoctoral research fellow at the University of Queensland, Australia, and worked on translating deep learning and computational techniques such as QSM to clinical application and enabling robust and reproducible MRI analysis. He's actively involved in the development of open-source neuroimaging software, including QSM-XT Toolbox and the QSM-CI Reconstruction Challenge platform. His work leveraged automation, software containerization, and open standards such as BITS to improve the reliability and interoperability of neuroimaging research.
All right, thank you very much, Benjamin. So in 2014, so 10 years ago, a survey at the University of Edinburgh found that 92% of researchers said that they use research software, and 70% of researchers agreed that it would not be practical to conduct my work without research software. Further, 56% wrote research software themselves, but only 21% of those had software development training. And so while this was 10 years ago, and these numbers may have increased and might be higher within the MRITogether community as well, I think it's prudent for us to reflect on how we're writing software and whether we can improve how we approach it. And this is also why it's great to participate in these sort of open science communities and hackathons that Mary was just speaking about. So this talk is meant to be educational. I'd like to share from the more technical side, what are the tools and techniques that you can use to write robust research software, and show how my research collaborators and I have benefited from them ourselves. And I want to show by example and hopefully demonstrate that some of these really software engineering techniques aren't necessarily as intimidating as they might have sounded at first. And while I use demonstration, I want to show that these ideas are also grounded in principles. And so I'll be referring to these principles called the FAIR principles and the FAIR for research software principles. So these were described in recent years to make digital assets more accessible, transparent, and reusable, to enable better collaboration and reproducibility across disciplines. It's about making and sharing research outputs in ways that maximize their usability and impact now and into the future. So for research software, FAIR means that software is findable, that it is accessible, interoperable, and reusable. And I'll bring some of these principles and criteria back throughout the talk. Within each of these principles, there are many different criteria, and I'm not going to go through all of them in detail, but some of them I will be reflecting on. So perhaps the most important foundation that we need to be on the same page about is that source control is really non-negotiable for writing robust research software. But luckily, 95% of us are already using source control for writing research software. It answers questions like who made specific contributions, which version of the code produced results, and beyond tracking changes, it helps with platforms like GitHub. They support collaboration through things like pull request, wikis, GitHub pages for hosting documentation, features like forks, issue tracking, and so on, that really make it easier to manage these open source projects. And so Git and GitHub are really going to set the stage for everything else that I'm going to be talking about today. There are other source control sort of centralized servers that you can use to store your Git repositories like GitLab. There's Bitbucket as well. But what we don't want to be using ever are these sort of cloud-based file storage platforms. And I've had workflows that sometimes depend on binaries that people have uploaded to these kinds of platforms, unfortunately. And they're not guaranteed to exist for longevity. And so then things start to break down. They're really just not designed for it. And there's even, I think, in this survey that I've cited here, I think it was 10% of software developers in research sometimes use collections of zip folders to manage their software versions. So we definitely don't want to be doing that. And this is also comes back to one of the FAIR criteria for reusability, and it's that software is associated with detailed provenance. So that just means tracking who contributed when, how did the software come to be. And so beyond source control, I'd like to touch first on testing. And we've heard about testing more today as well, but testing is really the only way to demonstrate that software is robust. And this comes back to these fairness principles as well. It's the way that we demonstrate that software is usable, that it actually can be executed. So there's a few different kinds of tests, and more than half of us are using unit tests. So this is the smallest type of test. Typically, you're testing individual functions or modules within a single programming language. Beyond that, we have integration tests. These are tests that are connecting often independent modules together and making sure that their APIs will communicate in the way that we expect them to. We also have system tests. These are very high-level tests that run from entire workflows from end to end, often on perhaps large or real data sets, to make sure that sort of the use cases are actually accounted for and they actually work, that the software installs correctly and so forth. And then lastly, there's regression testing. And regression testing kind of relates back to the other kinds of testing as well. This really just means rerunning your tests each time you make changes so that you can see if something from a completely separate part of your program has broken after introducing a new feature or change. And there's also user testing, which is something that is more difficult to automate, but there's some percentage that are using user tests as well. So among researchers, testing is perceived as important, but is underutilized. And so researchers report challenges due to lack of training in formal testing methods. So I'd like to talk about a few of the resources you could use for this, and sometimes limited tool support for testing. But so yeah, I'll be talking a little bit about how we can automate these kinds of tests. And fortunately, most of the popular languages in MRI research have very well supported test frameworks. So Python, for example, we have PyTest. MATLAB, there's a unit test framework in there. For R, there's TestThat. Julia, which is another scientific programming language, has built-in testing. For bash scripting, it's a little bit different and probably would rely more on ad hoc testing scripts. So these test frameworks like PyTest, they can really cover quite a majority of the kinds of tests that we might run. So they really excel at running these unit tests, possibly integration tests if we're testing modules that are in the same programming language. And they form at least part of our regression tests as well. But continuous integration, which I'll be talking about shortly, extends this further to cover system tests and a little bit more as well, which I'll talk about. But before we get to that, I'd like to just show some examples of what these kinds of unit tests might look like, what these kinds of tests look like, in case you have maybe never encountered them before. So if I have a really simple program that just can add or multiply, and maybe another program that can do some very basic kinds of conversions, I could write some unit tests using PyTest. And so for this, I'll write a few functions. I'll import the functions that I want to test, and I will test them. So I'll write functions that test that when we run them with certain parameters, we get the results that we expect. So I'm testing add and multiply, and I might write another script that will test these two different conversion functions. Integration tests, as I said, are similar, but they connect sort of potentially independent modules. So we can use our converter and our calculator together to solve more complex problems. Now, in reality, integration tests might test very different modules or may even involve integrating modules across programming languages. And for this, we usually can't depend on a single framework like PyTest, and we need something to closer to what we would use for system testing as well, which we can also talk about. So when you run these sorts of tests in PyTest, you'll usually get nice summaries that show which tests passed and which failed. If you're using an IDE like Visual Studio Code, it will show you this interactively as well. These exist for MATLAB and RStudio as well. You can run these kinds of tests. And sometimes, especially in MRI, our tests might rely on outside data. So for these, we might write what are called fixtures. So these are functions that provide data for our tests. And so here we've basically got a function that's creating an empty DICOM data set. So it's something that just has a dummy patient name, maybe some other metadata, and it returns it. We can then use that in our subsequent tests. So this is called a fixture. And we might also have tests that depend on slightly more realistic data. So we might write fixtures that pull data from servers like OSF. Maybe it would cache data locally so that if it already existed, we wouldn't need to re-download it again. So that's kind of what these tests can look like. And hopefully that seems fairly accessible if you haven't seen these kinds of unit tests before. But what I'd like to get into now is continuous integration. How do we actually automate all of this? So continuous integration is about running tests and other actions transparently using cloud resources. And 54% of researchers use continuous integration. And it helps to ensure reproducibility across another environment. If we can run our tests that sort of build our software and we can run them using cloud resources, we demonstrate that it actually works separately from the computer that we're developing it on. It saves local compute time, so some of your tests might take a while to execute. If you can use it with cloud resources, that frees you up to do other things. It reduces user error, so because we're automating this and it's always happening in a very consistent way, there's no way you can forget to run these tests if they run automatically, for instance, with every commit that you make to the repository or with before every release. And it does all of this transparently, which demonstrates the functionality for others and helps to build trust. And so this, again, comes back to this fairness principle that the software is usable, right? We're demonstrating transparently that the software actually works. And so there's a few different platforms you can do continuous integration with, the most popular being GitHub Actions, which I'll talk a bit more about. But there are other CI platforms like CI/CD on GitLab, Jenkins, Azure Pipelines for Microsoft. But by and large, GitHub Actions is what most of us are probably using. So if I have my little calculator program that I just showed before that I wrote some unit tests for on GitHub, so I've hosted this now on GitHub, I can go into Actions and I'll see that it's already suggesting certain actions for this repository because it's recognized that, well, this is a Python project. We'll see that we can configure tests for a Python package. So I will go in and configure that. And it creates this workflow. So this is a workflow that will be run every time we push on the main branch. So every time we make a commit and every time we merge a pull request, this test will be run. And it will test with Python, multiple different Python versions as well. So Python 3.9, 3.10, 3.11. Going a bit further down, we can see that this workflow installs dependencies if we've defined them. It does linting, which tells us about if there are syntax errors or undefined names and other problems with our Python code, and then it actually runs our PyTest test suite. So when we create that workflow, we can go back into Actions and we can see that the workflow has already run, right, 1 minute ago. So I can go into this and I can see that it was successful on 3.9, 3.10, 3.11. Going into that, I can see it actually was running my calculator, converter, and this little integration test that I wrote as well. And so now I've gone and introduced an error. I've messed up one of the assert statements in my tests, and it shows me exactly when that fails. And I can go straight into it and see why it failed as well. So this means that if I forget to run my unit tests locally, it will always show on the source code repository which tests are passing and which are failing. So these are our different kinds of tests, and we've looked at how test frameworks can run some of them and how to get this running in a continuously integrated way. But what about system tests? So again, system tests are about testing a full workflow or pipelines, the pipelines that we expect our users to be running. So checking that our software can install correctly and processes real data sets correctly. So for a quick case study, I'll have a look at QSM-XT. This is a QSM toolbox that I developed. This is for quantitative susceptibility mapping. This is a kind of MRI post-processing technique that measures magnetic susceptibility and biometals across the brain. And so for QSMXT, I've got workflows, much like the workflow that we just looked at in GitHub Actions, and I've added in some extra steps like setting up QSMXT. So this is an extra setup step that actually runs a script that I wrote that does a few things. So it basically installs QSMXT from the beginning. This is, kind of like the step that was installing Python. This time we're actually installing a container. So this is running using Singularity. As a later part of the workflow, it then runs a full system test. And this is running a script that does a few things. This script downloads some test data. It downloads it from OSF. Then it actually runs the command line interface in the shell. So it's doing multiple steps for this quantitative susceptibility mapping problem. After we've downloaded the test data, which is in DICOM format, it converts it into the brain imaging data structure using some scripts that we've included in QSM-XT as well. And then finally, it actually runs QSM-XT, and it does a whole lot of other things in here that we can talk about. But this is really the end-to-end system test. And so we can see this transparently. Anyone can go in and see this running. We can see it downloading the test data. We can see it running these different commands. We can see what version was used, what command was used, how many DICOMs it could see, how it converted it into the brain imaging data structure, and then later how it actually ran the code. And as well as this, that we can produce reports at the end of these system tests that actually show interactively images of our reconstructed susceptibility maps and artifacts that we can download that show what the results should look like. We have resource usage graphs as well that we use to validate that our parallelization is working correctly, that it's using the right resources that are available on the system. So those are some examples of system tests. And so only 27% of us are using these, but you can hopefully already see how by adapting the existing pre-made workflows that we have for our frameworks like PyTest, could allow us to validate this sort of end-to-end functionality of our workflows with just a little bit of extra work to sort of download test data, make sure things are installed correctly, and then run our workflows. And what I think is really great about writing system tests is that they double as documentation by example. So I actually believe that once your software reaches a certain level of complexity, that if you don't system test your software, well, can you even be sure that you know how to run it? Especially as the necessary environment or dependencies of your software change or become more complex. And so in QSMXT, I've documented examples of certain steps on the website in our documentation. So for instance, this shows how to install it on an HPC. And you sometimes see these little code snippets that show you, for instance, this one is showing you how to install it using this tool called Transparent Singularity for a high performance computer. And if we look at the markdown that was used to generate this documentation, we can see this step here, right? Install it via Singularity. It actually is inserting this code snippet from a separate file. And this separate file is actually the same file that's used for our system test. So in this way, we actually are validating that our documentation is correct because the code that we're showing here is tested. So these are some examples of continuous integration for these different kinds of tests. So what about the other side? That's continuous integration. What about CD? This is continuous deployment. So continuous deployment is really about automatically building and releasing software to users. I couldn't find any data about how many of us are using CD, probably less than 25% because that's how much are doing system tests. And what this is really for is, again, reducing human errors, automating the process of releasing software. This makes it more efficient, time efficient, a more consistent process. This also leads to higher quality releases because it'll be easier for users to navigate. We make sure that it is actually tested before we deploy it. Easier for users to find and access. And then ultimately, this helps to create impact if users can find and use it in the repositories that they are used to. And this comes back to another FAIR principle, that the software and its associated metadata is easy for both humans and machines to find. So are we deploying it to the right place? And accessible is retrievable by standardized protocols. So can you install the software using package managers and so on? So when we run continuous deployment actions, we automatically publish our work. And this could be in language-specific repositories like PyPy. It could be in system package repositories, like various Linux package repositories, container repositories like Docker Hub, or other deployments. We might deploy our documentation using GitHub Pages. We might run notebooks that form part of our documentation as well. But I might go back to this Python example to just show what this could look like to publish to a repository like PyPy. So if we go back to our calculator program, we'll go back into actions. And so I introduced this error before, but let's actually create a new workflow. And this will be to publish the Python package. And again, this is coming up as a suggested workflow for this repository. So let's configure this. So this is going to upload the Python package every time you create a release. And so there's instructions just a bit further below on how to set this up. But what it basically involves is going to the PyPy website, logging in, and going to this publishing section where you need to enter some details so that it knows that it can trust your repository and where it's being pushed from, right? We're pushing from GitHub. I gave it a name. I'm the owner. This is the name of the repository, and this is the name of the workflow. So you just fill out this form. Then you can go back to GitHub and create the release. So we create a release. We fill out some details. I'm going to call it version 0.1. This is our initial version of the software. So as soon as we create this release, that action becomes triggered. We can see that down here, version 0.1.0. Going into that, we can see the action running, and then it gets deployed to PyPy. If we go into this, we can see that it's actually now available at pypy.org at this particular URL. I can go to that URL, and I can see online that our tool is available. And so I could now go into Python and use this command that they've given back to me to actually install my package. And in fact, anyone can. So we can do a pip install. This is the Python package manager. I put in the command, right? It successfully installed my MRITogether demo. And in Python, I can now start to import my really basic functions that I developed and continuously integrated. So yeah, that's an example of what continuous integration could look like for PyPy, but there's the action templates are available for all of these other kinds of container repositories as well. And I encourage you to find out what is typical for the specific research sort of domain you're in, and consider where you look for tools. What do you use? So to sort of recap on CI/CD, continuous integration is about running tests and other actions using cloud resources. It demonstrates that your software is usable, which is an important FAIR principle. And continuous deployment automatically builds and releases your software to users and makes sure that your software is findable and accessible. I'll now take a little bit of a tangent and talk about software containerization and how that's important for robust and reusable software. So MRI analyses and software can be long and complex with many dependencies that they rely on to function correctly. And this often works because in our operating systems, we have package managers that help us keep everything compatible with each other. But when we, for example, update our operating system or we try to run unmaintained or unpackaged scientific software, then this starts to fall apart. We get missing libraries and dependency issues. So this is a reproducibility and portability problem. So, for example, there was this study on reproducibility of neuroimaging analyses across operating systems. They ran the same analysis with two different versions of an underlying dependency, but the same version of FreeSurfer. And because of the way that this glibc library does float point rounding, this actually led to significant differences in long analysis pipelines. So the organic solution to this problem is to have many research labs have adopted is to have a computer per project where they try to install the software once and then perform as little change as possible. But this isn't a good use of resources, and a hardware failure can be really problematic, and not updating a system can cause security problems. And because of this, installing and maintaining scientific software across different kinds of computers is really, really challenging. And so, could containers help? What is a container? So, software containers bundle software with their dependencies, and they use kernel features called namespaces and C groups to isolate processes from each other. So everything we need for software can be bundled together in a standardized container. To make it portable and reproducible so that it doesn't depend on the sort of system level libraries that you have on the machine. And so we can describe and publish these containers in registries like Docker Hub for others to find them and access them. And so all they need is a container engine like Docker or like Singularity to run it across all kinds of different operating systems. And so I'll touch now on a little bit of work done in my group in Brisbane with Stefan Bollman on the NeuroDesk project. And this is really a large international collaborative project. So NeuroDesk hosts containerized software that we call neurocontainers that you can reliably and reproducibly access across a range of different neuroimaging tools here, where there's over 200 gigabytes of neuroimaging software, but it's delivered in as Singularity containers that you actually stream using a file sort of system protocol called CVMFS. That's the CERN virtual machine file system, so that you don't have to actually download these containers fully to actually use them. So we've got a whole suite of different neuro containers available, and several different interfaces that you can use to access them. So there's a traditional desktop interface that you can actually run within a web browser. We've got a command line interface that you can run for, I guess, more advanced users that you also need for an HPC. And you can also run it using Jupyter Notebook. So across diverse computing environments. And this really is all supported by the community. So the community is able to contribute neuro containers to our repository. And if you have complex dependencies for your research software, I would encourage you to write a container recipe and then contribute it to NeuroDesk. And we have a guide for how to do this on the NeuroDesk website as well. And so at neurodesk.org, you can see the different ways that you can access it, right? You can actually run it in your web browser using cloud resources, using this tool called NeuroDesk Play, or you can install it on a whole host of different machines, from your local machine to HPCs and cloud resources. And so this makes all software, neuroimaging software, ready to go. We don't have these dependency issues because we're running using containers. This leads to reproducible analyses. And the base container for NeuroDesktop is only 1.5 gigabytes. So although it has access to over 200 gigabytes of software, it's very straightforward to set up. I mentioned that it runs on an HPC, and it can also run in a Jupyter Lab interface. So lastly, I'd like to just briefly touch on open standards. So, and this relates to one of the FAIR principles as well, that software is interoperable. So software reads, writes, and exchanges data in ways that meet domain relevant community standards. And so, of course, this helps with interoperability by having a seamless ecosystem. It helps with wider adoption of your software. supports reproducibility by minimizing unpredictability. If you're using predictable data structures, for instance, the brain imaging data structure, this makes it easier for people to reproduce your workflow, and easier collaborations if people are using a common language. So some standards in neuroimaging software, of course, we all will know about DICOM, NIfTY, the 3D analysis format, the brain imaging data structure, which has done a lot of work in standardizing the way we store neuroimaging data sets. So it creates this predictable structure that we can run on with all kinds of software tools that interpret bits. And so this predictable structure makes it easy for others to write analysis software and to scale easily, since BIDS datasets can represent large amounts of data. And so to that effect, there have been tools developed called BIDS apps. And so what BIDS apps try to do is to define a standardized interface to software that processes BIDS datasets. And so some well-known BIDS apps would include fMRI prep and QSI prep, for example. And so some of these other sort of, I guess, standards are, I guess, less standards and more community conventions. Things like NiPipe, which is a Python library for running long sort of chains of neuroimaging analysis sort of steps. We have boutiques for packaging containerized applications and giving them a command line interface that's standardized. We have OSF for hosting neuroimaging data. Neurodesk has its own repository of containers and so forth, and there's also other platforms like BrainLife that are sort of standardized among different sort of sub-communities of neuroimaging. And so following as many of these standards as you can where possible, I think will help make your software more adoptable and help it to have more impact. So with QSMXT, for example, I tried to adopt as many as I could that made sense, and that actually includes most of the ones that are here. So we read DICOMs, we convert them to the brain imaging data structure and NIfTY. It is defined with a BIDS app compliant interface, so it runs on BIDS data. It uses NiPipe to manage the workflow because QSM involves a long processing pipeline. So this helps to scale it up to different computing resources. We host our test data for this on OSF, which I showed earlier. And it's on Neurodesk and BrainLife as containerized applications. So I guess some takeaways that hopefully you can take for future projects. Some recommendations is to, I guess, put your project on GitHub as soon as you start it. If possible, make it public and choose a license. Keep a list of dependencies of your software and keep that list up to date. If your project has complex dependencies across multiple languages, you should consider writing a container recipe. Write tests often, especially when you reach milestones. Use continuous integration and deployment to keep your software reliable. You can use actions to run tests with each commit, publish your package with each release, and build software containers with all the dependencies available, and then deploy to whatever your domain-specific repository is for containers and so on. You should provide documentation using examples that could be derived from your system tests, and use example data that's hosted publicly on repositories like OSF. Use standard data formats like BIDS wherever you can, and establish frameworks like boutiques or NiPipe for running complex pipelines. Yep, thank you very much. I'd like to thank my group in Brisbane, Stefan Bowman's lab, and here at UT Austin, the Pestily lab.